Contrary to its seemingly vacant name, space is far from empty. Within its bounds lies a concealed structure, a force that permeates its very essence. This force, known as spacetime, is not a mere abstraction. It is as real and fundamental as any tangible entity. It serves as the connective tissue of existence, intricately weaving together the fabric of space and time. It is the silent orchestrator, guiding the dance of celestial bodies and shaping the destiny of galaxies. From the dawn of time to the present moment and beyond, space-time has been the silent architect of our reality. It governs the trajectory of stars, the flow of time, and the very essence of existence itself. Every event, every particle is bound by its invisible embrace. But what exactly is space-time? How does it exert its influence over our past, present, and future? From the dawn of creation, space-time has been an active participant in the cosmic drama, guiding the evolution of galaxies and the birth of stars. Its influence stretches back to the very origins of everything, playing a pivotal role in the unfolding story of our universe. To unravel the tale of space-time is to unravel the tale of our universe itself. To understand its beginnings, its evolution, and its ultimate fate, we must journey back to a time before time, to the moment when the universe burst into existence in the cataclysmic event known as the Big Bang. This momentous event marks the birth of both space and time itself. Picture, if you will, the universe in its infancy, a minuscule speck of energy suspended in the vast expanse of space-time. In the blink of an eye, this infinitesimal singularity erupts into a frenzy of expansion, giving rise to the universe as we know it. This rapid expansion, known as inflation, is a concept that stretches the limits of imagination. Within the blink of a cosmic eye, a region smaller than an atom burgeons exponentially, dwarfing even the size of galaxies. To grasp its magnitude, envision a grain of sand swelling to encompass the breadth of the observable universe. What's more astonishing is that during this epoch of inflation, the universe defied the laws of physics as we understand them. It expanded at a velocity surpassing even the speed of light, a phenomenon that challenges the very foundations of our scientific understanding. In this tale of cosmic inception, the universe's journey from nothingness to boundless expanse is a testament to the incomprehensible forces that govern our existence. As you ponder such mysteries, you might find yourself questioning the notion of anything surpassing the speed of light. Indeed, in the realm of physics, this holds true, except when it doesn't. The cosmic rulebook dictates that within the bounds of our universe, nothing can traverse space faster than the speed of light. However, in the phenomenon of inflation, space itself undergoes a remarkable expansion, sidestepping this cosmic speed limit without violating any laws. Imagine the universe in its infancy, at the precipice of the Big Bang, a moment when space and time erupted into existence, hurtling outward in all directions. It was not matter or energy racing through the cosmos at breakneck speeds, but rather the very fabric of space itself unfurling in an extraordinary growth spurt. Yet this expansion was far from uniform. Within the expanse of inflating space, subtle variations emerged, with some regions slightly denser than others, albeit by a fraction of a percent. These tiny fluctuations acted as the seeds from which galaxies would eventually sprout. Inflation, like a cosmic sculptor, magnified these density disparities, stretching them into vast expanses and laying the groundwork for the formation of galaxies, stars, and ultimately, life itself. Thus, through the dance of expanding space-time and the orchestration of cosmic forces, our universe took shape, weaving a tapestry of wonder and intrigue. As the drama unfolded, variations in the inflation of different regions in space ushered in a new chapter of cosmic evolution. In the cooling aftermath, a profound transformation took place. Energy coalesced into matter. Within the denser pockets of the cosmos, matter began to congregate, drawn together by the irresistible pull of gravity. These regions, laden with more mass than their counterparts, held sway over the very fabric of space-time itself. You see, mass isn't just a property of matter. It's a cosmic architect, sculpting the landscape of space and time. The more mass accumulated in a single location, the more profoundly it warped the surrounding space-time. Consider this. Even as we converse, I, with my modest mass, exert a subtle influence on the curvature of space-time. Indeed, the notion of space as a static backdrop fades away, replaced by a dynamic interplay between matter and the curvature of space-time. Space bends, curves, and warps in response to the gravitational pull of matter, shaping the cosmic landscape in ways both subtle and profound. We witness this celestial choreography as the very grid of space-time curves and contorts in response to the presence of celestial bodies. What we perceive as gravity is, in essence, the manifestation of this curvature, a force unlike any other, intimately entwined with the fabric of space-time itself. Imagine, if you will, a trapeze artist gracefully descending into a safety net. At first glance, the net appears as a pristine, orderly grid, yet upon impact it yields to the weight of the performer, distorting and bending to accommodate their presence. Much like the trapeze artist's net, space-time undergoes a similar transformation in the presence of mass. Matter, nestled within the cosmic expanse, warps the very framework of space-time, creating undulations that ripple across the cosmos. The greater the mass, the more pronounced the distortion, a principle that lies at the heart of gravity's enigmatic grip on the universe. But grasping the true nature of gravity and space-time proves to be a daunting task, a puzzle whose intricacies continue to elude even the most brilliant minds of our time. In the chronicles of scientific history, one name stands out among the rest. Einstein, whose revolutionary insights reshaped our understanding of the universe. He dared to envision space not as an empty void, but as a dynamic entity capable of bending and warping. Einstein's groundbreaking theory proposed that space and time possess their own intrinsic properties, a vitality that extends far beyond mere emptiness. This dynamic interplay, he suggested, is what we recognize as gravity, the force that binds us to the fabric of space-time. Indeed, the denser the concentration of matter, the more profound the gravitational pull, and the deeper the curvature of space-time. This fundamental connection lies at the very heart of our physical reality, shaping the contours of the universe we inhabit. But while we have unlocked some of the mysteries of space-time, much remains veiled in uncertainty, a source of both fascination and frustration for scientists. We can describe how space-time behaves within the confines of the laws of physics, yet the deeper intricacies elude our grasp. It was within the crucible of the Big Bang that space-time and energy converged, birthing the infant universe and laying the groundwork for the cosmos we behold today. Yet, from these primordial ingredients, how did the intricate tapestry of galaxies, stars, and planets emerge? How did space-time orchestrate the grand symphony of cosmic evolution? These questions linger on the horizon of our understanding, beckoning us to delve deeper into the cryptic realm of space-time. Across the vast expanse, matter weaves itself into a colossal cosmic web, a structure of unfathomable complexity. Galaxies and their clusters adorn the filaments and sheets of this cosmic architecture, as if guided by an unseen hand. This architect, it seems, is none other than space-time itself, the very fabric of the universe. From the grandeur of galaxies to the minutiae of atoms, space-time shapes and molds the everything, binding together time and space in a seamless continuum. Indeed, the universe is not merely composed of matter and energy, it is composed of space-time, a substance that expands and contracts, warping and distorting as celestial bodies traverse its expanse. It is the essence of the cosmos we know, the canvas upon which the grand drama of creation unfolds. Yet, grasping the true nature of space-time is a daunting task, an abstract concept that eludes easy visualization. To comprehend its influence, scientists employ a myriad of tools, observing the universe in various wavelengths of light. And while we cannot directly see space-time, its effects are palpable, distorting as objects move through it, warping and shaping the very fabric of reality itself. Consider for a moment the journey of your car as it traverses the undulating terrain of our planet, ascending hills, descending valleys. In much the same way, the shape of space-time governs the trajectory of light and matter through the universe. The principles at play are elegantly simple. Any object with mass imparts its influence upon space-time, causing it to curve and warp. This curvature, in turn, dictates the motion of matter, a phenomenon we recognize as gravity. It is through the interplay of gravity and the curvature of space-time that matter coalesces, forming larger and larger structures across the expanse. Yet, in the early story of the universe, the landscape of space-time bore little resemblance to the world we know today. As the first seeds of matter emerged, they began to sculpt the shape of space-time, bending its contours in subtle but profound ways. Wherever mass gathered, space-time bowed under its weight, creating regions of increased curvature. In this galactic dance, the bending of space-time beckoned matter to gather in its embrace, fostering the formation of ever grander structures. These places, rich with matter, cast deep impressions upon the fabric of space-time. As the mass within these regions swelled, so too did the gravitational wells they carved, drawing in more matter with an insatiable appetite. This relentless cycle of attraction birthed stars, galaxies, and the many structures that define our universe. Within the fiery cores of these stars, nuclear fusion forged heavier elements, seeding space with the building blocks of planets and life itself. Over eons, these elements coalesced into celestial bodies, each bearing the imprint of the ancient fluctuations in space-time. Indeed, the expansion of space-time laid the groundwork for the grand tapestry of the universe we behold today. Galaxies, stars, planets, and life itself all owe our existence to the cosmic dance of matter and space-time. The mystery of space-time persists, eluding even the most brilliant minds of science. While we have gleaned insights into its behavior, its true nature remains shrouded in darkness. Then, in a momentous breakthrough in 2015, a revelation: the detection of gravitational waves, ripples in space-time generated by cataclysmic events. For the first time, we bore witness to the symphony of space-time. The universe is permeated by the invisible fabric of space-time, a silent sentinel guiding the futures of celestial bodies. Though elusive, this tapestry occasionally reveals glimpses of its influence, offering tantalizing clues to its mysteries. In the year 2016, astronomers witnessed a peculiar optical phenomenon resembling a cosmic halo. What appeared as a mere trick of the light was, in fact, gravitational lensing, a phenomenon where space and time are warped into a cosmic lens by the gravitational pull of massive celestial objects. At the heart of this revelation lies a distant red galaxy, its gravitational field distorting the path of light from a blue galaxy over 7 billion light-years away. Through this cosmic lens, the hidden blue galaxy is unveiled, its light bent and magnified by the gravitational forces at play. Gravitational lensing serves as a testament to the profound influence of space-time on the cosmos, offering astronomers a unique window into the hidden depths of the universe. It is a reminder of the intricate interplay between matter and space-time. Across the expanse, gravitational lensing is a consequence of the immense gravitational influence exerted by massive objects such as clusters of galaxies. These behemoths warp the very fabric of space-time to such a degree that light traveling from distant objects is forced to bend around them. This bending of light, a true warp in space-time, occurs as mass from the foreground galaxy curves the surrounding space-time, a manifestation of gravity's invisible hand. In its journey through this warped space-time, light follows the contours created by the mass, resulting in a distorted path similar to the bending of light through a piece of glass. The consequence of this gravitational distortion is profound. When observing a distant galaxy through a galaxy cluster, we witness multiple images of the same object, often forming arcs and circles reminiscent of glass lenses. While gravitational lensing offers a unique window into the effects of space-time on light, it remains an indirect observation of this elusive entity. But could there be another avenue through which we can perceive space-time's influence? A method not reliant solely on sight, but on sound. Recent insights suggest that space-time itself possesses material qualities, akin to the iron sheet before us. Just as this metal can distort under the weight of a heavy object, so too can space-time bend and flex. And much like waves propagating through this iron sheet, space-time can carry waves, albeit of a different nature. To set this cosmic fabric in motion requires a force of tremendous power, a metaphorical hammer to strike the cosmic anvil. And perhaps through the exploration of these ripples, we may unlock new avenues of understanding, allowing us to perceive the hidden depths of space-time in ways previously unimaginable. These ripples, known as gravitational waves, are disturbances that reverberate through space-time itself. To unleash these waves requires nothing short of the most cataclysmic events in the universe, events like the collision of two black holes. When these titans collide, the resulting release of energy sends shockwaves rippling through space-time. By the time these waves reach us on Earth, they have diminished to almost imperceptible proportions. But scientists at the LIGO Observatory achieved a monumental feat. They detected the elusive gravitational waves. It soon became clear that this was an unprecedented milestone, a direct detection of gravitational waves by human-made instruments on Earth. The discovery of gravitational waves not only validated decades of theoretical work, but also opened a new window into the hidden realms of the universe. It was a testament to human ingenuity and perseverance, reaffirming our capacity to unravel the mysteries. What makes this discovery even more astonishing is that the frequencies of these waves align with the range of sounds discernible to the human ear. As two black holes spiral closer and ultimately collide, we perceive a distinct change in frequency, a swooping crescendo that echoes the dance of these celestial giants. Listening to these ripples in space-time has granted us an unprecedented tool to probe the depths of the universe, unveiling a realm of existence previously beyond our perception. Just as Galileo's telescope revealed previously unseen wonders in the heavens, gravitational wave astronomy has bestowed upon us an entirely new vista of the cosmos. But while gravitational lensing and gravitational waves shed light on the interplay between gravity and space, we must not forget the other half of the equation: time. In the intricacies of space-time, gravity not only distorts the fabric of space, but also warps the flow of time itself. Though we often think of time as immutable, it can be bent and twisted under extreme conditions. In such circumstances, the very notion of time as a constant becomes blurred, opening the door to the tantalizing possibility of time travel. Once viewed merely as the passage of days, time has evolved into a concept far more profound. It is not just a feature of existence, but an intrinsic aspect of reality, a constituent thread woven into the very fabric of space-time itself. From the moment of the Big Bang, time has marched inexorably forward, interwoven with the expansion of space to shape the universe as we know it. When matter exerts its influence on space-time, it not only distorts space but also orchestrates temporal shifts. This phenomenon transforms the abstract concept of time into a tangible aspect of our reality, a river whose flow can be bent and redirected by the gravitational pull of massive objects. Just as gravity warps the contours of space, it also manipulates the pace at which time elapses, a mind-bending revelation that underscores the sheer complexity of space-time. At the forefront of this are black holes. Near the event horizon of a black hole, where gravitational forces reign supreme, time itself begins to warp and contort, slowing to a crawl as if caught in the grasp of an invisible force. This peculiar phenomenon, known as time dilation, forms the basis of the twin paradox, a thought experiment that explores the repercussions of venturing close to a black hole. Imagine two twins, born simultaneously, with one embarking on a journey near a black hole while the other remains on Earth. As they reunite through video calls, they would observe a stark disparity in the passage of time, one aging at a drastically slower rate than the other. Should the twin near the black hole succumb to its gravitational pull and cross the event horizon, time would seemingly grind to a halt from the perspective of the distant observer. Yet, paradoxically, should the twin manage to escape the clutches of the black hole, they would return to find the passage of time on Earth had outpaced their own, an extraordinary testament to the nuances of space-time and the profound influence of gravity on our perception of time itself. In the shadowy embrace of a black hole, the boundaries between science fiction and reality blur into an enigmatic realm where the fantastical notion of time travel becomes curiously feasible. While journeying into the past remains a figment of imagination, traversing the corridors of time towards the future emerges as a plausible prospect within the confines of our universe. Though the prospect of time travel remains confined to speculation, the influence of space-time on our daily lives is palpably real. Indeed, it is gravity that holds the key to unlocking the mysteries of time's ebb and flow. Descending towards the Earth's surface, time slows to a languid crawl, while ascending to greater heights accelerates its relentless march. This intriguing phenomenon is not confined to the esoteric realms of theoretical physics, but manifests in the rhythms of our everyday existence. Intriguingly, this gravitational time dilation extends beyond mere theory, as advances in precision timekeeping allow us to discern subtle variations in the flow of time. In a world where every tick of the clock holds significance, the disparities in temporal experience become all the more poignant. Indeed, this curious interplay between gravity and time yields unexpected consequences, where the lofty denizens of penthouses age at a faster rate than their grounded counterparts, an ironic twist in the cosmic narrative that underscores the immutable bond between space, time, and the human experience. At an altitude of 12,000 miles, a fleet of global positioning satellites orbits the Earth, their precise movements and timing crucial to the functionality of navigation systems worldwide. In our modern era, reliance on the global positioning system has become ubiquitous, with many relying on the reassuring guidance of their smartphone apps. These devices leverage signals from 4 satellites to pinpoint our location on Earth, a feat made possible through meticulous timing. Embedded within each satellite lies an atomic clock, a marvel of precision timekeeping. But in the weightless expanse of orbit, where gravitational forces are weaker, these clocks tick at a slightly faster rate than their terrestrial counterparts. Without accounting for this relativistic effect, the accuracy of the GPS system would rapidly deteriorate, rendering it useless in a matter of mere hours. It is a testament to the relentless march of progress that we continually correct for these subtle discrepancies, ensuring the seamless functioning of the GPS system day in and day out. As we peer into the abyss of cosmic time, we are confronted with the sobering realization that space-time will ultimately dictate the universe's fate, from its birth to its inevitable demise. For nearly a century, astronomers have been captivated by the revelation that the cosmos is in a state of perpetual expansion. Every corner of the universe is receding from one another, propelled by the inexorable march of time. This choreography is evident in the light emitted by distant celestial phenomena, such as Type 1a supernovas. These stellar explosions, known for their consistent brightness, serve as cosmic mile markers, allowing scientists to gauge the vast distances between objects. Over decades of meticulous observation, astronomers have witnessed firsthand the stretching of light as it traverses space-time. Initially, it seemed intuitive to assume that the gravitational pull of matter scattered throughout the universe would act as a tether, gradually slowing the pace of expansion over time. However, in a paradigm-shifting revelation in 1998, astronomers made a startling discovery. The expansion of the universe was not decelerating as expected, but accelerating at an unprecedented rate. This revelation defied conventional wisdom, challenging our understanding of the fundamental forces that govern space. For the first 7 billion years of history, the expansion of the universe appeared to be gradually losing momentum, but the influence of gravity seemed to wane, as if the very fabric of space-time itself were being propelled apart by a mysterious force. The implications of this discovery are profound, casting doubt on our conventional understanding of the universe's evolution. Are we witnessing the gradual erosion of gravity's influence, or is there an unseen force at play, pushing the boundaries of cosmic expansion to unprecedented limits? Across our universe lies a mysterious force, one whose behavior defies conventional understanding, the entity known as dark energy. Much like the unseen currents of space-time, dark energy permeates the cosmos, constituting a staggering 70% of the ingredients that shape our reality. But despite its ubiquity, the true nature of dark energy remains shrouded in obscurity. The term dark serves as a poignant reminder of our profound ignorance regarding this elusive phenomenon. Unlike ordinary matter, which we can observe and quantify, dark energy eludes our grasp, existing in a reality beyond the reach of our senses. It manifests as an invisible force that injects energy into the very fabric of the universe, driving its relentless expansion with unfathomable vigor. But the essence of dark energy remains a mystery, an elusive puzzle that continues to confound the brightest minds in cosmology. Its peculiar behavior defies the laws that govern ordinary matter, exhibiting a repellent force that counters the attractive pull of gravity. While ordinary matter succumbs to gravity's embrace, coalescing into celestial bodies and structures, dark energy stands aloof, impervious to the dance of attraction. As we grapple with the mysteries of dark energy, we are left with more questions than answers. Could it herald the emergence of a new force in the cosmic tapestry, one that transcends the familiar confines of gravity? Or perhaps, like space-time itself, dark energy emanates from the very essence of the universe, a silent architect shaping the destiny of all that exists. An interesting hypothesis emerges, a notion that dark energy may be an inherent property of space-time itself. Could it be that the very structure of space possesses an energy of its own, an energy driving the universe to accelerate in its relentless expansion? Dark energy remains a cryptic enigma, its true essence eluding the grasp of even the most astute cosmologists. But what does this reveal for the future of our universe? If dark energy continues to fuel the accelerating expansion of space-time, the consequences are concerning. Galaxies will drift ever farther apart, the fabric of the space stretched thin by the relentless march of acceleration. As the universe hurtles towards an increasingly desolate future, the once vibrant light of cosmic creation will fade into darkness, its brilliance dimmed by the inexorable advance of time. This grim vision, known as the Big Freeze, represents the ultimate endgame of the universe as we know it, a fate marked by desolation and decay. While the prospect may seem bleak, it is a destiny that lies in the distant horizon, a fate to be pondered by future generations, untold eons from now. And in the interim, we find solace in the knowledge that our universe's freeze is a fate that lies beyond the bounds of our mortal existence. Recent research hints at a far more unsettling prospect than even the concept of the Big Freeze. Imagine a future where dark energy grows in strength, surpassing the gravitational pull of entire galaxies. The formidable grip of black holes would succumb, torn apart by the relentless force of dark energy. The very fabric of the cosmos would be shredded in a cataclysmic event known as the Big Rip. In this apocalyptic scenario, clusters of galaxies would be the first to fall, followed by the dissolution of galaxies like our own Milky Way. Eventually, even our solar system would succumb to the unstoppable force, torn apart in the cosmic upheaval. In the waning moments of existence, the Earth itself would be consumed by explosive fury, reduced to vapor in the final throes of destruction. The fate of our universe hangs precariously in the balance, its future dictated by the mysterious forces that govern its evolution. Will it meet its end in the icy grip of the Big Freeze, or will the cosmos be stretched apart in the cataclysmic fury of the Big Rip? Or perhaps the end is not truly the end, but merely the prelude to a new beginning. In the grand story of cosmic evolution, space-time plays a dual role, shaping both the genesis and the demise of our universe. And as we delve deeper into the mysteries of these pivotal events, we find ourselves confronted with a perplexing conundrum, a flaw in our understanding of the Big Bang. Picture the universe in its infancy, a tumultuous epoch where all matter, every galaxy, planet and star, lay within an infinitesimal point of unimaginable density, a singularity. According to the precepts of Einstein's general theory of relativity, these singularities are a natural consequence, yet the realm of the infinitesimal is also governed by the laws of quantum mechanics. Quantum mechanics, our bedrock understanding of the subatomic realm, dictates that nothing can truly attain infinite density or minuteness. It presents a paradox, a contradiction to the existence of singularities. In the subatomic domain, where particles, fields, and forces interact in intricate dances, the notion of an infinitely dense point defies comprehension. If singularities are indeed prohibited by the laws of quantum mechanics, then the very foundation of our understanding of the Big Bang is called into question. Without the existence of singularities, the very epicenter of our cosmic genesis, our conception of the universe's birth, undergoes a seismic shift. After years of inquiry, scientists present a concept that harmonizes the principles of both general relativity and quantum mechanics, quantum spacetime. This proposed theory holds the promise of unraveling the enigma of the universe's earliest instance. By melding the intricate dance of quantum mechanics with the expansive canvas of spacetime, it aims to shed light on the primordial epoch that birthed our universe. The quest for a quantum theory of gravity that sidesteps the pitfalls of singularities is paramount. Such a theory could redefine our understanding of the Big Bang itself. Imagine a universe where the birth of the cosmos was not a cataclysmic explosion from nothingness, but a graceful transition from the remnants of a preceding universe. In this scenario, the Big Bang is not a singular event, but rather a culmination of the cosmic cycle. Before our universe burst into being, another universe existed, its fabric of space and time contracting rather than expanding. In this narrative, the cosmos unfolds as a continuum, each loop flowing seamlessly into the next. Consider an alternative to the bleak visions of cosmic endings, a universe not destined for rips or freezes, but for cycles of collapse and rebirth. Picture an ancient universe, expanding majestically before succumbing to the relentless pull of gravity, folding back upon itself. As space-time contracts compressing into a minuscule speck, conventional wisdom would suggest a singularity, a point where all known laws of physics break down. But what if instead of a silent demise, the universe experiences a resurgent burst of vitality? As matter densifies under the immense pressure of collapse, a powerful force emerges, repelling the cosmic fabric and triggering an explosive rebound. Reigniting in a dazzling display of cosmic fireworks, a new round of expansion, a fresh beginning akin to a new Big Bang. In this perspective, the familiar narrative of the Big Bang becomes a postscript to a greater cosmic drama, a reflection of the universe's enduring resilience. Could it be that our very existence is intertwined with the ebb and flow of an eternal cycle of birth, death, and renewal? If we inhabit a bouncing universe, the implications are profound. It suggests the tantalizing possibility of an infinitely old universe, devoid of a singular beginning. Instead, we may be mere actors in an infinite cosmic theater, participating in an unending procession of cycles within a meta-universe beyond our comprehension. Our grasp of space-time remains tenuous at best. It's a concept that eludes complete understanding, yet its undeniable importance is evident. Without it, our very existence would be impossible. Space-time isn't just an abstract notion, it's an integral part of the fabric of reality itself, woven into the very essence of the universe. To truly unravel the mysteries of the cosmos and comprehend its ultimate destiny, we must delve deeper than mere observations with telescopes. We must grapple with the fundamental nature of space-time. The enigmatic nature of the universe can be bewildering. The concepts we encounter in the study of cosmology and relativity often defy intuition, stretching the limits of our imagination. It may sound like the stuff of science fiction, but rest assured, it's all rooted in scientific truth. We inhabit a universe that's infinitely more intricate and breathtaking than our minds can fathom.